So when it rains, the rain, if it's in a significant amount, can carry away the soil with it and form a slide that is called mudslide. So the density of which depends on the amount of water, or the ratio between the water and the soil that is in it. And as people in this area know, the consequences of mudslides can be serious. This was a video that was recorded in Malaysia as a consequence of the mudslides that were taking place here last year. And as you can see, there are serious consequences for the transportation system that can be completely interrupted. And there are consequences for the area where people live that can be flooded. As you can see here, this is an aerial vision of the area. So there is a significant impact on the life of every day. And there was another video in US where you have the mudslide here that went onto the highway. And as you can see, it covered the whole motorway. Here there is the motorway on this side and the railway on the other side. And as you can see, the mudslide brought water, and you can see here a pond formed, and mud. And as a consequence, all the traffic was stuck into the mud up to a level of 1 meter, meaning that all these means of transportation could not move. As you can see, the whole wheels are covered with mud, and meaning that the whole highway has been closed down, and there was no means to communicate the two cities that are adjacent. So how can we monitor mudslides? Well, the easiest way would be using satellites. Now, there are quite a lot of satellites. So this is a picture that shows the position of satellites around the Earth in the last few days. And as you can see, there are loads of them. And most of them are for environmental uses. So as you can see, this is the geostationary distance. There are quite a lot of them. And there are some that are much closer. We could use some of them for environmental monitoring. And there is one that is called the A-Train, which is particularly famous because it monitors the water content in the air and the water content down on the ground. So in principle, using this train that is constituted by 6 satellites, it's possible to determine what is the water content at different levels on the air. But that's not all of it, because if we consider mudslides, it's not only a consequence of climate, but it also depends on the geology of the area. So if we consider the climate and the geology, then we can map the hazardous areas. So if we have a hilly area where the soil is quite low density, and we predict to have very high rain in levels in that area, then we have high hazard. There is also another way to look at it. Sorry. There is another way to look at it, which is from the impact point of view. So if we have a look where people live and the geology of the area, then we find areas that are more prone for damage. So clearly, if there is a mudslide in the middle of the forest where nobody is there, I think the interest is limited. While on the contrary, if there is a mudslide in the outskirts of KL, clearly there is much more interest in investigating that. So if we unify both of these, we end up with a map of the hazard area and a map of the vulnerable area, so where people live and there is a significant hazard. So if we join these, then we do have a map of risk. And that is what is interesting. So from here you can see that it's not only the climate, but we also need to have information about the morphology of the terrain and the distribution of the population or industrial activities. Now there is a problem. The problem is that the data is not complete. For example, we don't have data about the geology of every part of the country. And on the other side, sometimes the data is not timely. So we don't have really instantaneous measurements of the water levels. So we have quite a lot of uncertainty on these two. And additionally, we also have an uncertainty in the theory. So there is not really a perfect theory which gives the exact value for which we have mudslide. So this has many variables, including the density of the terrain and so on. And so it's difficult to have a good prediction of where the slides are going to be. So what we can do is actually to monitor in real time. And optical fibers can be useful because they have low loss. They have a loss of 0.15 dB per kilometer. So this means that we can actually have a sensor that is positioned 100 kilometers from the station. So this means that if we have a station in Kiev, for example, we can monitor an area that is 100 kilometers around it. And we can have lots of different types of sensors. One is the point sensor, so which monitors a single point in space. And the other one is a distributed sensor, which monitors along a certain distance. This is a point sensor that was developed about 15 years ago and relies on the bending of the fiber. So the idea is that if we have a slide, we have also cracks in close proximity. So we can put part of this device on one side of the crack and part of the device on the other side of the crack. And when the crack opens, the two moves apart, inducing a bend in the fiber. So this will result in a loss at a specific distance in the fiber. By monitoring constantly the loss, then we can monitor the movement of one part of the ground with respect to the other. Now, so there are lots of ways to maximize this effect, like playing with the geometry of the fiber, with the refractive index distribution, and so on. So by designing a specific fiber, it's possible to maximize the sensitivity. Another way is actually to monitor the vibrations. So if we have a major event, like for example, a significant infrastructure like a highway is falling apart, there is an acoustic trace associated to that. So we can use optical fiber seismometers to measure the vibrations to associated to these events. So in this case, this is a fiberized seismometer which relies on light being inserted in optical fiber. Here, light is split in two parts. Half goes this way, half goes this way. If this is right in the center, then the back reflection here go back to the detector, and if everything is designed well and it's in quadrature, we don't detect anything. When this is moving, then the optical path on this side is different from the optical path on this side, and then intensity is measured at the detection system. So when this is moving, this is the seismic mass, the mirrors associated to it will move as well. And so in this way, it's possible to determine the vibrations of this system. Now, this is a point sensor, but still allows to determine the vibrations in a certain part of the country. Now, this might be useful if you want to monitor earthquakes. Can be useful to monitor this major stuff, but you would need to place one seismometer in close proximity to an area that you expect to be affected by such a big event. It doesn't seem to be very effective. We have developed something similar using microfibers, so fiber with a small diameter. And the idea is that making the sensor so compact, we can position it in a lot of different places. But above all, what is important about this seismic device is that that the sensitivity is 100 times higher, so we can detect vibrations that are 100 times smaller, or 2 orders of magnitude smaller than the ones recorded with an equivalent fiber device. And another way to look at the problem is actually not to detect the vibrations in the soil, but to the vibrations associated to the water falling. So if we have a rain, each drop will introduce an acoustic signal. So we can use this signal to detect the amount of water. So according to the size of the droplet, we will have a different acoustic signal. So by counting the number of acoustic signals that we have and making an integration, then we will be able to determine how much water has fallen in a specific place. This is an acoustic sensor that we developed in my lab, and it's very, very simple. It's based on a plastic tube that is just 1.5 centimeters in length and about 2 millimeters, I seem to remember, 3 millimeters in diameter. And then there is a microfiber wrapped around it. This material is very, very soft, so that if there is a change in the pressure, like in acoustic pressure, like in the case of acoustics, then there is a change in the shape associated. And this change in shape implies a change in intensity. So when there is an acoustic wave coming here, there is a sinusoidal change in the pressure. And this means that there is a compression and an expansion of this tube. This is the system that we use to monitor these acoustic traces. So we use a loudspeaker. I mean, it was not that expensive, a cheap loudspeaker. And we had the sensor that was connected to a source and to a detector. So in this way, we had part of the light that went this way and part that went this way and back. So as before, there can be constructive or destructive interference. And when the shape of this is changing, also the interference pattern is changing over here. And by monitoring the change in the pattern, interference pattern, then we monitor what is the change in shape and therefore the acoustic trace of this device. This seemed to work very well at very, very small pressures as well. In fact, it was even capable to determine people whispering tens of meters away. So it's definitely capable to measure the acoustic trace of a water droplet that is falling down. Another sensor that we developed in Southampton that can be used for environmental monitoring is the gas-liquid interface. This was developed because our oceanographers wanted to monitor the amount of life at 3 kilometers underwater. So the idea is very, very simple. As Aziz mentioned earlier on, what we can measure with optical fibers is a change in the refractive index. So what we've done is we took a fiber, we cut off the end so that we had a sharp tip. And because of the sharp tip here, part of the light that is injected is reflected. Now, the fraction that is reflected depends on the difference between the refractive index here and the refractive index here. When there is air, there is lots of reflection because the refractive index is 1.5 here and 1 here. So the refractive index difference is large. When there is water, on the contrary, there is smaller refractive index because water has a refractive index of 1.33. So if I have a look at what happens when this tip goes from gas, so from liquid into the air, I will have small reflection into the liquid, and this increases when it goes into a gas. So we use this to perforate bubbles, and this is the kind of profile that we would observe in the reflective intensity when our tip goes through a bubble. And this is the experimental recording that we had. So these are about 11 bubbles, and each time the tip goes through a bubble, there is one spike. We have done that measuring the number of bubbles, and our oceanographers could relate the number of bubbles to the concentration of living microorganisms down in the ocean. This is part of the experiment that we've done. So we had a wave generator, and then this is the wave that was generated, and then we moved the sensor across it and monitored the concentration of bubbles at different depths. This is a magnification of an area of the wave generator. So it was not so big. I mean, you can see this is about 80 millimeter, 8 centimeters. So it was a tiny wave, and we were able to scan across the wave and determine the concentration of small bubbles. This has been deployed in the South Atlantic onto one of the ships, and to be honest, I lost track of it. I hope it's still working. Another way to use microfibers for sensing is actually to exploit the field that is outside. So a microfiber is basically a fiber, this is a fiber, that has a smaller diameter. So it's connected by two transition regions to the fibers, and the light, which is injected in the core in a normal fiber, it expands, and then it propagates in the cladding, in the microfiber. And it's interesting because here you have part of the light which is outside. And by definition, this outside section can interact with the surrounding environment, meaning that we can use that to sense whatever is going around. So one idea is to coat this section with a functionalized material so that we can increase the selectivity of our sensor. So by coating with a selective anti-DNA material, for example, we can select DNA types. We can coat it with the gel and measure the humidity. We can coat it with palladium and measure the hydrogen. So according to the functionalization that the microfiber has, it would be possible to determine the concentration of a well-determined biological agent or a chemical agent. Clearly, we can also combine this and put it into an interferometer. Here you see a humidity sensor where we have two different types of microfibers that are spliced to a polymeric microfiber. So instead of functionalize the microfiber, another idea is to make a microfiber from a different material. This was made by polyimide, I seem to remember. And, from PAM. PAM is a polymer. When the humidity is changing, the refractive index is changing, and so the loss is changing as well. So by monitoring the loss, it's then possible to determine what is the concentration, the humidity around that device. And as you can see, the response of this device is pretty good, with response times which are in the region of seconds or so. But there is another way to look at the problem, which is actually try to exploit distributed sensing for light monitoring or environmental monitoring. So in the past, we used the fiber only to deliver the signal to the sensor that was positioned tens of kilometers away. But there is the possibility to use it as a sensor or an intrinsic sensor, like Ken mentioned earlier on. So in this case, we have a source, we have a coupler, and we launch a pulse into the fiber on the test. Part of the signal is then back reflected, goes through a filter and to a detector. So this is the light travel, and according to the time it takes for the light to come back, we can understand whether we are investigating this position, or this position. So there will be a relation between the time of flight and the position along the fiber. This technique is called optical time domain reflectometry. It's possible to do the same with FPGs, like Ken mentioned earlier on. But so this is the kind of trace that we will observe. So if we launch light into the fiber and we detect the backscatter light at the same frequency, we will have a spike where the light is injected, and then a decrease with the distance. And this will have then a reflection at the end. This is a typical pattern for ray light scattering. If we have changes in between, then we will have changes in the reflection. So for example, a change in the temperature implies that this is going to go up or it's going to go down. Now, if we use ray light, we can monitor temperature changes. So this is the schematic of one of our ray light systems. But if we use different ways, we can also monitor other features. Now, Raman is one of the most commonly used for the measurement of temperature. But Brillouin, which is mainly used in Southampton, is very interesting because the peaks do not depend on the temperature only, but the temperature and the strain. So we have the intensity of these peaks and their position that depends on two variables. So if we then measure the intensity and the frequency shift, then we can determine the temperature and strain. So why is this important? It's important because the strain is what we can use to determine the acoustic trace. So if, so this is the inverse process. So if we measure the intensity and the frequency shift, then we can get the temperature and the strain induced. Now, if we imagine to have a droplet that is falling down, this will induce a strain. So if we are capable to measure the strain along the fiber, we will be able to determine what is the number of drops that have been falling along the distance of the whole fiber. And this is because each raindrop is associated with an acoustic trace. So if we do an integral in a specific place, then we can determine what is the amount of water that is falling at a specific distance. And this is interesting because you can determine the movement of large amounts of water. So we can not only determine the drops that are falling, but also the mudslides. So when the soil starts to move, there is a strong acoustic signal that is associated to that. So we will be able to determine whether we have just one drop or a significant change. This could be used as an early warning system, like for example the one for the tsunami. And it's interesting because in Malaysia you already have a system of optical fibers that are already in the soil. So using these as sensors might be a good idea. We have something similar in Britain. So we have the optical fiber system that runs by the railway. And this system for telecom is also used for sensing. So it's possible to determine, for example, when carriage goes off, when we have soil that is going onto the railway. And we also monitor when people are crossing the railways when the train is coming. We can determine the train that is moving onto the rail and whether the train has some problems. So we can imagine to use this system of network to determine whether there are significant issues into a specific area. The interesting bit here is that we don't need to have lots of stations everywhere, but the stations that are here are enough to monitor an area that is in excess of 100 kilometers of radius. So as I said, this could be used for real-time acoustic monitoring and early warning of disasters. Now, if we look into research, how can we improve the status of these sensors? At the moment, fibers are used in multiplexing modes, so we have lots of different wavelengths that go into our fibers, and demultiplexing at the other side. They carry lots of information, but they are limited by the fact that they have only one core. There are different ways to improve it. One is to have a multi-core fiber. So we have been working together with a Japanese company and the OFS in the United States to multi-core solution. So instead of having just a single core, we can have lots of different cores. This is clearly beneficial for telecom because it's possible to increase the amount of data that is transmitted. But it's also interesting for sensing because when the fiber is spent, each core will provide a different signal. So it's possible to get information about the movement, the shape of the fiber. So using this type of fibers will allow us to investigate what is the change with time in the ground. So using the same network that we already have available, we can monitor whether there is any displacement in a selected area. Or we can go for multi-mode, and that is what we have been working recently. So instead of having just one mode, we have many modes at a specific wavelength. And for these, we have been working on a specific device that uses microfibers that is transforming a single mode injected in a single mode fiber into a selected mode. It can be the fundamental mode or it can be one of the higher order modes coming out from the few mode fiber. And we successfully demonstrate the excitation of the first higher order mode and the higher order modes like B21 and B02. These are devices that work over a wide range of wavelength, and as you can see, the performance is more or less the same. So the next is actually to use these for environmental sensing. So in conclusion, I'm sorry I'm running late. Mudslides seem to have lots of complex, they are affected by lots of events, and there are lots of factors that are fundamental in the determination of mudslides. Optical fibers could be useful for monitoring mudslides or environmental monitoring in general. And this type of sensor can be divided in point sensing, which can be associated to the detection of a small movement in a selected area, or distributed sensing, which in my opinion might have more success. And these could be used to predict what's going to happen, or more likely to trust them, to trace them, so to know in real time whether a major event is taking place. Thank you. If you have any questions?
Thank you, Prof.
So I'd like to open the floor for any questions. Yes.
Thank you, Professor Gilberto. So, since when we taper the fiber, the diameter we want normally 5 to 6 micron, or maybe 10 micron. So, what method you use to deposit other material on it? Let's say you want to deposit ammonia or you want to deposit graphene. What type of method you use to deposit?
Each material has a different method. For example, if you want to use palladium, palladium is used for gas detection. In this case, you do it from vapor phase. If you want to deposit gels, for example, for humidity detection, you just dip the taper inside, or you can even have a dispenser, drop dispenser, and so you drop onto the fiber and you let it slide down. We use that, for example, for Teflon. So according to the material that you want to do, you have a different treatment. For biological and chemicals, for example, we have a functionalization process. So we start with silanization, and after that we attach a specific receptor. So we have done DNA recently, and there are 3 layers. So there is silanization, which is the first one. There is the chemical that is detecting a part of DNA in between, and then there is a linker in between. And this has been optimized, has been taken from the planar technology. And how do we do that in practice? We take the microfiber, we put it in a tube, then we inject with a syringe the different chemicals. So first of all, the one that is used for silanization, then we take it out and clean. Then we put the second one, that is the linker, and then the third one, which is the selective part. And after that, we take out the microfiber from the tube, and the sensor is ready.
Thanks, Prof. And I have one more question. I was very interested in the rain sensor. So the method you have used, if I'm not mistaken, that is acoustic sensor. So
Yes.
if I'm not mistaken, what I mean, like you put the microfiber inside the plastic box, and if you put the plastic box outside.
We haven't done that, but that is something that, in my opinion, we could do. Okay, we have done the acoustic sensor. So the acoustic sensor is just a tiny bit, is a tiny device, more or less this size. So if you leave it here on the table, it will be able to detect the noise that is coming from everywhere. Me talking, you talking, even people breathing, we can detect that. Now, if you imagine to have a sensitive area, like for example, a metal square on top of it, that reacts in a specific way to water droplets, then you can record only that acoustic trace. because you need to be selective. When you have an acoustic sensor, you record all frequencies from 20 Hertz up to, we have gone to nearly 100 kilohertz, so ultrasonics. And if you have a metallic membrane on top of it, you have a very peculiar trace. So you have just selected wavelengths, and because selected frequencies, and because of that, you can detect one drop from a flight that is flying by or from me speaking. So if you look at that trace, then you can detect the number of droplets, and the intensity will tell you how large the droplets are. You probably need to do some calibration, but at the end you will be able to determine the number of drops and their size. So you will be able possibly to determine the amount of water that has come down in a determined unit of time.
Prof, have you tested in your laboratory that how efficient the system is if you compare your result and the conventional method? Let's say normally we already know that maybe today there is 5 millimeter rain.
Right.
But if we use your sensor and measure it, how much is the discrepancy or how exactly?
As I said, this is a proposal, so we don't have really a rain sensor. We have an acoustic sensor, and the acoustic sensor was able to detect people whispering at 10 meters of distance. So it's very sensitive. So imagine to have somebody at the door that is whispering, and we could detect that. Even more interesting, in my opinion, is the distributed acoustic sensing, because we have this system that is going to 10 kilometers and can determine people talking at different distances. So it's a microphone that works at every distance. So if you have a fire that from here goes, I don't know, 100 kilometers from here, you can determine each single drop that is falling from here up to there. So you have a huge amount of data, and that is the big problem, data processing. But you have a high reliability system that allows you to detect in real time over a long distance. So when you have these large areas to evaluate, like a whole country, you need to have a distributed system. I mean, you can have a quasi-distributed system, but distributed system is better because it provides you basically a total overlap with your country. So satellites might be good, but they don't provide all the information. Acoustic sensing, for me, is pretty good because it has the dual function of monitoring potentially the amount of water that's coming in and the presence of big events like, for example, slides. These have a very strong acoustic trace, and if you can detect people talking, you can definitely detect a mountain that is falling down. So.
Prof, in that case, let's say somebody is playing the music, somebody, let's say the vehicle is moving on the road, still they will give some vibration.
It's very different.
Yes. So how you will differentiate all those?
Is you analyze the spectrum. So the frequency is very, very different. If you consider, for example, a slide, it has components at short frequencies, so 20 hertz, 10 hertz. If you have a vehicle is higher frequencies. If you have a loudspeaker from a car that somebody listening to the music, you have components at kilohertz as well. So according to the spectrum, you can determine whether it is somebody walking, whether it's a tractor, whether it's, you can detect different types of events. We have done that as an experiment in our corridor. So we had the acoustic sensor on the floor, and we could detect different people walking in the corridor. So when you walk, you have a trace that is different from me. So you can even recognize the different people walking in the corridor from the acoustic trace. And it's really easy to detect a person from a trolley being pushed. And it's even easier to determine a rainfall from a major event. So it's quite easy. The big issue is the amount of data that you generate, because you have a system that is working at kilohertz. So each time you provide a huge amount of data because you have the frequency. So it's a huge amount of data, and you can